Imagine a power source so abundant, so clean that it could fuel humanity for millions of years. No carbon emissions, no long-lived radioactive waste, just pure energy from the same reaction that powers the sun. This is fusion energy, and after decades of research, we are closer than ever to making it a reality. But there's an unexpected twist. As AI models like ChatGPT, Gemini push our power grids to their limits, it's AI itself that's solving the control problems that have kept fusion out of reach. The race is on to unlock the power of the stars before we hit the wall on energy capacity. Training GPT-4 required 50 to 60 million kilowatt hours of electricity. That's enough to power 160 average American homes for an entire year. Now multiply that by the billions of queries processed daily across ChatGPT, Claude, Gemini, and other AI systems. According to the International Energy Agency, data centers consumed 415 terawatt hours in 2024, about 1.5% of all global electricity. By 2030, that number will more than double to 945 terawatt hours. That's equivalent to Japan's entire annual electricity consumption. And AI is the primary driver. In the United States alone, data center electricity demand will surge by 130%. Grid operators are already warning that up to 20% of planned data centers could face delays due to inadequate power infrastructure. This growing energy challenge is one reason tech companies are investing heavily in new power sources, including fusion. Fusion has been 30 years away for 70 years. The challenge has always been the same, getting more energy out than you put in. But December 5, 2022 changed everything. Scientists at Lawrence Livermore National Ignition Laboratory achieved what humanity had been chasing for 6 decades, scientific fusion ignition. 192 lasers fired simultaneously at a target smaller than a peppercorn. The intense energy compressed deuterium and tritium fuel to pressures and temperatures found only in the cores of stars. The result? 2.05 megajoules of laser energy delivered to the target produced 3.15 megajoules of fusion energy, an energy gain of 54%. For the first time ever, the fusion reaction itself produced more energy than was delivered to the fuel, and this wasn't a one-time success. Subsequent experiments in 2024 and 2025 achieved even higher yields, proving this is repeatable science. After 70 years of trying, humanity finally demonstrated net energy gain from fusion. Here's where it gets fascinating. Fusion plasma is inherently unstable. It fluctuates in milliseconds. If it touches the reactor walls, the reaction stops instantly and the extreme heat can damage the containment vessel. Human operators simply cannot react fast enough to keep the plasma stable, but AI can. Google's DeepMind developed a deep reinforcement learning system that monitors 90 measurements 10,000 times per second. It adjusts the voltage on 19 magnetic coils in real time with reaction times under 1 millisecond. This system successfully controls the variable configuration tokamak at EPFL in Switzerland, maintaining complex plasma shapes that humans could never stabilize manually. In 2024, DeepMind released Thorax, an open-source plasma simulator that runs millions of virtual fusion experiments before reactors even power on. And in October 2025, Google partnered with Commonwealth Fusion Systems to use AI to optimize their Spark tokamak. The ultimate irony: AI is both creating the energy crisis and solving the control problem that makes fusion possible. AI powering the technology that will power AI's future. Fusion requires two fuels, deuterium and tritium. Deuterium is abundant. You can extract it from seawater. No problem there. Tritium is the challenge. Tritium is radioactive with a half-life of just 12.3 years. It barely exists in nature. A single fusion power plant would exhaust Earth's entire tritium supply in 1 year. The solution? Fusion reactors must breed their own fuel. Reactors surround the plasma with a lithium-containing blanket. When high-energy neutrons from the fusion reaction hit lithium atoms, they produce new tritium. If designed correctly, a reactor can produce more tritium than it consumes, becoming fuel self-sufficient. In 2025, MIT's BABY experiment achieved the first-ever measurement of tritium breeding, validating that the process actually works. But here's the catch. Only 1 to 5% of tritium actually burns in the plasma. The rest must be continuously captured, recycled, and reused. Tritium breeding at commercial scale has never been demonstrated. It's one of the critical challenges that must be solved. Fusion creates conditions hotter than the surface of the sun. Something has to contain that heat. The diverter is the part of a fusion reactor that handles plasma exhaust, the waste heat and particles from the fusion reaction. During normal operation, diverter surfaces face heat fluxes of 10 to 20 megawatts per square meter. That's like concentrating the heat from 10 to 20 industrial furnaces onto 1 square meter. But during sudden plasma instabilities, heat loads can spike to gigawatts per square meter in under 1 millisecond. That's enough to vaporize most materials instantly. The solution is tungsten. With a melting point of 3,422 degrees Celsius, tungsten has the highest melting point of any metal. ITER's diverter uses 300,000 individual tungsten components, each precisely cooled to prevent melting. But tungsten is brittle. It cracks under thermal shock, neutron bombardment degrades it over time, and plasma erosion slowly wears it away. Researchers are developing advanced materials and coatings to make tungsten more durable, but surviving these extreme conditions remains one of fusion's toughest engineering challenges. While ITER, the massive international government fusion project, aims for first plasma in 2034, private fusion companies are racing to deliver power to the grid much sooner. Commonwealth Fusion Systems, backed by Bill Gates and Google, is building Spark, a compact tokamak outside Boston. Spark targets demonstrating net energy by 2027 and delivering power from their ARC commercial plant in the early 2030s. Google has already signed an agreement to purchase power from the first ARC plant. Helion Energy has the most ambitious timeline. Backed by Sam Altman, OpenAI CEO, and with over $1 billion in funding, Helion aims to deliver 50 megawatts to Microsoft's data center by 2028. That's an extremely aggressive goal, especially given fusion's long history of delayed timelines. In total, over 50 private fusion companies worldwide have raised $7.1 billion. The big question is whether these companies can overcome the final engineering hurdles and deliver on their ambitious timelines. If fusion succeeds commercially, it would provide virtually unlimited clean energy. No long-lived radioactive waste, no carbon emissions, just abundant power from the same reactions that light the stars. The irony is striking. AI is driving unprecedented energy demand while simultaneously helping solve the plasma control problem that have kept fusion out of reach. But the final challenges, the material science and the fuel logistics, must still be proven at commercial scale. The next 5 to 10 years will be critical. We'll see whether companies like Commonwealth Fusion and Helion can deliver on their ambitious timelines, or whether fusion will continue to be 30 years away. But the science is real, the investments are substantial, and for the first time in 70 years, fusion energy feels within reach. If you found this helpful, subscribe to the channel for more deep dives into AI infrastructure and technology explained.